to the second day of Cognitio 2021. You're very welcome and very happy to have you here with us today. We have a very long, interesting day of very cool talks. The first one is going to be presented by Daphne Demekas. She's a developer at Nested Minds Network. And Ben White, who is a Leverhulme-funded PhD student at the University of Sussex. And Mark Miller, who is an assistant professor at the Center for Human Nature, Artificial Intelligence and Neuroscience at Hokkaido University in Japan. And the presentation is going to be given today by both Ben and Mark. The title of the presentation is Artificial Empathy, Active Inference, and New Collective Intelligence. Before I give you the floor, Ben, I just want to make a note that at the end of the talk, those of you who would like to ask any questions or comments, please do come to the Q&A, which is here on the left where it is marked as Q&A. Just come and line up, and when you want to ask a question, just make sure that you are standing on the circle, because otherwise you won't be able to be heard. So just on that note, I'll give the floor to Ben. The floor is yours.
Thanks, Inez. So I just want to make sure, can everybody see my slide and hear me okay? Good. Okay, so, whoops. Okay, so yeah, it's, I think a good morning is in order to most people listening to this. I just want to say thank you for having me, and it's important for me to say before I get started that this is very much still a work in progress, and it's been a collaborative project from the beginning. So myself and Mark Miller are carrying out this work with Daphne Demekas and also Katsunari Miyahara, who is at Hokkaido with Mark Miller. And I just want to say Mark Miller is here, and he'll be joining me in the Q&A after the talk. Now, since this is an active inference conference and we're already in day 2, I'm actually going to skip over kind of intro to what the framework is and how it works. And what I want to do instead is tell a kind of a story about how we see the active inference framework influencing new and exciting approaches in designing affective computing devices. So, affective computing is a pretty rapidly growing research program, and it aims to create computing and robotic devices capable of recognizing, categorizing, and responding intelligently to human emotions. So this obviously draws on quite a wide interdisciplinary body of research, including neuroscience, psychology, philosophy, computer science, and engineering. And it's also important to say that the term affective computing itself was coined by Rosalind Picard, who is an MIT professor, and she now runs the MIT Affective Computing Lab. That's Rosalind Picard there with the cover of her original book. And I want to give some examples of affective computing. Most of these are from the MIT lab. So researchers there have been looking at a range of different uses for this kind of technology, including how it might operate in the classroom to aid teaching and learning, how affective interfacing in cars might make for better improved road safety, and how affective computing could be used for therapeutic interventions like JIBO, which is the little screen and camera thing you can see at the bottom of that slide. That's actually been used and tested in dorms of undergraduate students at MIT. And another example is the little yellow guy on the blue background. That's Wobot, as in W-O-E, Wobot, who's another therapeutic intervention that uses natural language processing. So if you want to check out lots of examples of this stuff, then the MIT Affective Computing Lab has their own website, and it's very, very cool. But for now, though, the majority of the current deployments of affective computing have been in industry, including sectors like recruitment and marketing. So, for example, the company Unilever is currently using a form of emotion recognition tech to analyze the nonverbal cues and responses of people during interviews, and then this software decides who they hire and who they don't. And I think Amazon have recently started using something quite similar as well. Now, because of the increasing prevalence of this in industry and business, it has attracted quite a lot of criticism, both in terms of its functionality and in terms of some what we think are very well-founded ethical concerns surrounding its use. So people in the know are kind of skeptical about this. So for example, the insurance company Lemonade recently caused a Twitter outrage when it merely hinted at the fact that it might start using emotion recognition technology to detect fraudulent claims and that kind of stuff. So current versions of emotion recognition have been shown to have some really serious shortcomings, actually. So some researchers in affective science have claimed that these systems are just founded on highly questionable science and some badly misguided assumptions about what emotions are and how they work, going so far as to label these systems a kind of neo-phrenology. So Lisa Feldman-Barrett in particular has been very critical of what she terms a theory of basic emotion, which underpins most of these systems. So in a nutshell, this theory just says that humans have 6 to 8 basic emotions, and that these emotions are kind of universally expressed through discrete, readable sets of facial expressions. And so in a recent interview, Barrett stated that, quote, "There are some companies that just continue to claim things that can't possibly be true. Based on published scientific evidence, our judgment is that these technologies shouldn't be rolled out and used to make consequential decisions about people's lives." Now, there are a range of other ethical concerns. So Aberba Behani has argued that current systems, which are trained on very large data sets, are inherently conservative, and they propagate any biases or prejudices that are present in the data that they're trained on. So this can result in systems which are, for example, exhibiting racist or sexist tendencies, and there are lots of examples of this, unfortunately. So emotion recognition systems themselves have been shown to perform much worse on non-white faces. And there's a really disturbing study by Lauren Rue, which I've put up on the slide there, that confirms this. Moreover, Behani and others have recently pointed out that these data sets are now so large that the people that are using them, the entities that are using them to train their software, don't even know what's in there. And in a recent study, Behani found that there was just a range of kind of prejudiced or highly offensive material in there. And finally, many of these systems are subject to the kind of worries about opacity and black box kind of worries that afflict quite a lot of AI technology generally. But clearly, this technology is being used to make quite consequential decisions about people's lives. And so therefore, we think that it's pretty vital that this technology is at least underpinned by the strongest theoretical commitments. And so I want to be really clear from the outset that our goal in this talk is not to justify the wholesale use of affective computing in all areas. So we're not going to argue or suggest that what we suggest here today is going to solve all of these concerns. And this is really important to say, because even if what we're going to describe shortly is a promising way forward, and obviously we think it is, and even if theoretically all of this technology could be perfected, then there might still be very principled reasons to think very carefully about when it's deployed, how it's deployed, and who it affects. So what's the problem with it? Well, the major problem that we suggest in our paper is that the current paradigm in affective computing is very problematically disembodied. So while there's a huge buzz today about building emotional or kind of quote unquote empathic robots, all that boils down to, in most cases, is just building artificial artifacts equipped with emotion recognition software, coupled with some form of decision making. So suggesting, for example, like at Unilever, who gets fired, who gets hired. So in these cases, the emotional or affective side of things is really just very superficial. So these aspects don't play a significant role in the actual computing processes that are driving the interactions. So seen in this way, these approaches really are based on a foundation of seriously outdated cognitive science. Because now we know, of course, and we've known for some time really, that affect, cognition, perception, action, these are all dynamically co-evolving together. So for example, Luis Pessoa has argued that the prevalent view of emotions and affect as being somehow separate from cognition, having unique neural fingerprints, is problematic for a number of reasons. So he argues that complex cognitive emotional behaviors have their basis in dynamic coalitions of connected brain regions, none of which should be conceptualized as specifically affective or cognitive. And moreover, Pessoa emphasizes that these complex cognitive emotional dynamics are inherently linked with action, with how an agent acts in a given environment. And this intrinsic link between affect and goal-directed behavior is something that I'll return to pretty soon. So if we're taking human emotions and affective interactions, including empathy as a blueprint for designing affective computing devices, we need to think much more seriously about these important and complex dynamics. And so one way that we think you can do this is to bring active inference into the picture, which, as we know, integrates all of perception, cognition, action, and affect into one fluid, dynamic, and embodied system for minimizing prediction error. So we think that by using active inference as a theoretical basis for affective computing, it's going to result in machines that are functionally more impressive, and it might even offer avenues for potentially addressing some of the ethical concerns that I mentioned earlier. So we get two things right off the bat when thinking about introducing active inference into affective computing. So first, active inference offers a unique, shared, and transparent computational currency, which is made up of a suite of theoretical and mathematical tools that's going to allow theorists, neuroscientists, and machine learning researchers to all collaborate very closely on these issues. And second, it puts action up front in helping to solve our understanding of the world and each other. So consider just how crucial action is in human interactions. So we're constantly using actions to elicit responses, to probe, to test, to gauge how other people might be thinking or feeling. So for example, if you're on the subway and you see someone scowling at you, then you might decide to flash them a quick smile, just to see to test what's going on, because it might be the case that they just have a kind of resting scowl face, or it might mean that the scowl actually means something and we might then decide to kind of move carriages. So another example that I know that I've experienced and a lot of other people probably have is being in a job interview where the people interviewing you are deliberately hiding their emotions to remain neutral. And this can be quite stressful for us. And so we might kind of modulate our tone of voice or drop in a joke just to kind of try and get some information about how other people feel about this in that moment. So much of what we know about human emotion and how we navigate emotional situations is the result of this kind of testing and this kind of action. And importantly, this kind of active testing is central in figuring out all those kind of important contextual cues that dictate what an action or an expression means. So we do not inflexibly apply patterns from data like the current versions of emotion recognition do. We adapt on the fly, and we use cues in our environments and atmosphere to make sense of things happening in the particular moment. So just consider the stranger scowling at you again, but this time imagine it's taking place on a hospital ward, where you know that everybody's likely to be in quite a lot of pain. The meanings of these conveyances can change dramatically depending on the context. So context really is king. And actively probing is so crucial for getting context right in emotional interactions. And so this is, it's exactly this kind of active probing in order to get to better model and understand the emotions of specific others in specific situations that's kind of surprisingly lacking in current versions of affective computing. And so this, to our minds, is a major stumbling block for the current paradigm. So we already have some fantastic work out by active inference researchers, including Samuel Vassier and colleagues, on how we come to understand each other through exactly this kind of active process of reducing uncertainty. And so I want to highlight one example of where we see this gap between humans and disembodied AI in terms of dealing with context, and that is selective attention. So it's quite a pervasive problem in AI design that current systems don't tend to look at the same regions as humans do. So the question researchers are asking is, how can we make this search pattern more human-like? And how will this result in more accuracy? So successful selective attention is all about filling gaps in the observer's knowledge about where to look to get the most kind of bang for your buck in terms of reducing uncertainty. And typically researchers have thought that this is to do with humans just having a much wider kind of experience set and bigger knowledge base than neural nets. But we suggest that they may also have better machinery for gleaning through actively predicting, testing, and confirming what matters most in a scene. So the way we build up these models, as we've been saying, isn't only by passively perceiving, but by continually and actively probing. And this includes overt actions like saccading and moving, and also internal dynamics like precision reallocations. So this is one major benefit of a more fully embodied affective device, one that has available to it kind of manipulatable eyes, necks, heads. It's going to be able to physically manipulate its own viewpoints, just like humans do. And so it will be able to drink in a higher quantity of relevant details within the physical environment. And in the robotics community, this is known as active vision, and it's increasingly seen as absolutely vital to building intelligent systems. So one of the major benefits of applying the active inference framework to building affective computing devices will be this ability to actively forage for information to resolve its own uncertainty. And here that uncertainty is about somebody else's emotional states. So through current approaches to affective computing, they don't have to do this. Action-driven learning through reduction of uncertainty comes as part and parcel of active inference. So one corollary benefit worth mentioning, I think, is of this much more active approach, is that devices would actually have the benefit of needing much smaller data sets with shorter training times, because the device would be able to autonomously select the data that best optimizes the model in a given context. So this might just be one step toward addressing some of the concerns that Birhani and others have had about the problems that are kind of inherent in very, very large data sets. But from a practical standpoint, making these additions means that we'll just have to move beyond building affective computing devices that are basically lumps of plastic or just make use of camera phones. And so to begin to build properly embodied devices, we'll need humanoids with sophistic representations of the face, which are able to act fluidly and quickly, adapting in real time to the dynamics of conversation, action, and environment. So, kind of speaking of adapting fluidly in real time, in cognitive robotics today, an important question is how artificial agents learn their internal models in order to interact efficiently with the world around them and with other people. We've already talked about how important embodied action is to learning about other people's models under active inference, but we suggest that affectivity in the form of prediction error dynamics may be a key element in motivating and directing this kind of embodied epistemic foraging in artificial agents, just like it is in humans. So what that means, in other words, is what we're suggesting is affective computing devices would ultimately benefit from having internal affective dynamics of their own. Although many different computational models have been proposed for building intrinsic motivation into artificial systems in order to generate these kind of exploratory behaviors and curiosity, existing approaches have agents choose actions according to some internal measures related to the novelty or the predictability of anticipated situations. So the main difference between what's offered in active inference and these existing approaches is that in active inference, this intrinsic motivational architecture is based on the relationship between prediction error and affect. So according to recent work in active inference, affect is, at least in part, a form of second-order information within the predictive system itself. So this second-order information informs the system about how well or how poorly prediction error is being reduced over time relative to expectations. So in short, when we feel good when we do better than expected, and we feel bad when we're doing worse than we expect to, at reducing prediction error. And these feelings, this affective feedback, informs us about how things are going relative to those expectations. These second-order states also play an important role on modulating the level of confidence or precision that the system has in its own actions and beliefs. And of course, this seems to make intuitive sense, because when we do better than expected at reducing error, we feel good, and this good feeling helps to reinforce our confidence that whatever it was that we were doing, those current action policies and predictions are good ones to implement again in the future in similar contexts. So in this way, error dynamics serves to keep an agent flexibly and sensitively tuned to opportunities for success within our environments, and as our skills and abilities evolve over time. And notice here that agents outfitted with a sensitivity to error dynamics will naturally be curious. So they're going to be drawn to situations where the most error can be reduced reliably, because that's where the best feelings are going to be found. And those places tend to be at the edge of one's familiarity. So neither too well known, where there's going to be too little error, nor too complex where there's too much error and we become frustrated. So crucially, aerodynamics play a role in helping to direct and enhance learning. So prediction error and its reduction rates signal the expectations about the learnability of particular situations and helps to guide attention and prioritize learning, making the updating of our models much more efficient. So we have already seen this sort of optimal error engagement show up in curious robots. So Oidire and Smith is a good source here, where they train robots to seek out optimal levels of complexity because that's where the most learning can take place. And specifically, active inference approaches have begun to be used in real-world robotics. And there's some really, really great proof of concept in the work of Guido Schilassi, Bruno Lara, and Alejandra Siria, who have actually built robotic systems using this kind of internal machinery of prediction aerodynamics. And indeed, their work has shown how robots equipped with aerodynamics are better able to manage uncertainty by fluidly selecting adaptive actions in an environment when compared to more traditional approaches. So these artificial agents that are equipped with internal aerodynamics are better able to learn and then autonomously select the proper prediction error strategy in a given situation by allowing an agent's valence, which is that second order information, to weigh and motivate the selection of whatever might be the most suitable behavior. So this work also showed that aerodynamics provided a way for artificial agents to navigate the temporal aspects of goal selection, which is to say that when to engage with a goal, how long to persevere, persevere when things aren't going right before quitting, and so on and so on. So notice that affect here is intrinsically related to goals, arising when differences between expected and actual rates of progress occur. So to give a kind of cute real-world example, when my niece tries to reach the sweets in the cupboard and she fails, she might persevere for a given amount of time. She might see if first there's a way that she can use a stool to get a leg up or something. But when this strategy fails, inevitably the frustration builds and she might start to cry, at which point she's trying to rope someone else into her crime of stealing the sweets. And when this fails, she might ostensibly abandon the mission and run to her mum for a cuddle, which kind of viewed through this kind of aerodynamics framework is her engaging emotionally to potentially recruit someone else into getting the sweets for her. So we suggest in our paper that by introducing these aerodynamics into affective computing devices, we'd see devices not only motivated to flexibly and curiously implement new policies for action, which in this case would mean to learn more about other people's emotional states, but biomimetic devices implementing very similar kinds of affective motivational mechanisms that we see in humans. So this new wave of affective computing devices would not only recognize and respond to human emotions more efficiently, but it would actually have, in some sense, an internal emotional affective structure of its own. So lastly, and most interestingly, and definitely most speculatively, we want to explore the possibility that these kinds of devices, now equipped with this internal, proactively expressive body and something of its own affectivity, might be able to enjoy the kind of model synchrony with their users that we see emerging in the case of human interactions. So recent work in active inference on communication dynamics highlights this kind of synchronization as part of coming to understand one another. So in their paper, A Duet for One, Carl Friston and Christopher Frith have used simulations of songbirds to show that a generalized, and this is a quote from the paper, generalized synchrony is an emergent property of coupling active inference systems that are trying to predict each other. So in very rough terms, what they demonstrate is that according to active inference, meaningful communication between agents requires that these agents are sufficiently able to model one another and then model the other person modeling them, and so on and so forth in an infinite regress. And agents that are able to do this by making and testing predictions can come to synchronize their internal generative models. So as noted in the paper by Daphne, Demekas, Friston and Parr, quote, in the context of emotion recognition, this demonstrates the possibility of synchronizing the internal states of the device and its user, such that the device and user are both attending to and attenuating sensory information in order to properly cause and predict each other's emotional states. So I suggest that everybody that's interested in this kind of model synchrony checks out the two papers I just mentioned by Friston and Parr and Daphne and colleagues, just for some more information on the possibility of humans and robots understanding each other's emotional lives in that way. And it's worth noting here that for this sort of synchrony to occur between a human and a robot, their mutual predictions need to form this kind of closed loop. So that would mean that the emotional artifact would have to have some form of interoceptive signals, and it would have to act in ways that reflected those signals. So of course, this is all very speculative, but as we learn more about the brain and we learn more about emotions and we build a better understanding of these hidden states and these internal mechanisms, this kind of model convergence between a device and a user, we think becomes at least very plausible in theory. And we also think that building artifacts capable of this type of model synchrony with their users could have a number of potential benefits. So first, consider this form of synchrony within the context of therapeutic interventions. So when the artifacts model is able to sufficiently converge on the user's model, then when there's an anomaly in the user's predictions, such as there is in cases of things like depression or anxiety, the device would be able to understand how those predictions are generated and also predict what kinds of sensations or actions might help to alleviate them. And it's interesting that this is essentially what cognitive behavioral therapy is already trying to do. And second, in the action-orientated approach to affective computing that we've been talking about, the drive was largely epistemic. So that's to say that the artifact is trying to reduce uncertainty relative to modeling the user's emotional states. But once we have the possibility of humans and artifacts establishing this form of synchrony, it will begin to become possible for the artifact to install prior preferences about what agent states might be preferable, such that the artifact might actually be able to begin to steer the emotional synchrony to specific ends. We do want to flag a cause for concern here, though. These kinds of affective devices would still be subject to the kinds of concerns that exist around current systems, which is their abuse by powerful entities that might use this technology to oppress and control vulnerable groups. So in the case of these active inference devices that have this kind of model synchrony, there's a speculative concern there that they might make highly effective manipulators. Nevertheless, though, outside of these therapeutic settings, this sort of model cohesion could also set the stage for empowering a broad range of improved human-AI collaborative work through addressing the so-called value alignment problem. So very briefly stated, the value alignment problem is a worry that AI systems may, due to some unforeseen oversight, maximize some quantity that they value to the detriment of some quantity that we value. So this is essentially the kind of worry that underpins a lot of our sci-fi worries, sci-fi situations like Skynet and The Matrix. But by synchronizing and sharing a generative model and similar embodied affective mechanisms, what's good for a user will also be good for the device. And when the user is doing worse than expected, then so is the device. So the device will monitor its user and adjust its own precision profiles accordingly. And it's worth noting as well that active inference devices will not only rely on the same kinds of problematic data sets, they will not only rely on the same kinds of problematic data sets mentioned earlier. So by not relying on them, they'll possibly circumvent the possibility of picking up these hidden patterns of prejudice. But it's also worth saying that devices that are synchronizing models with individual users would obviously be prone to picking up any nasty attitudes or prejudices that that particular user already has. So basically, what we have here, we think, to our minds, is at least an initial and admittedly quite speculative, the building blocks of designing a much more authentically empathic AI. And this could also potentially be the basic requirements for safer and more effective collective and collaborative intelligence that could emerge between humans and machines in the future. And that's it. Thank you very much.
All right. Thanks so much, Ben, for this extraordinary talk. I will now open the floor for the Q&A. So if there's anyone that would like to come and ask a question, please come to the Q&A on the left. I think Shannon is coming in the first. So Shannon. Yeah, I think.
Station spot on this.
There you go.
Thanks for this talk, Ben. This has been really fascinating. And I'm interested in also how AIs create emotional art. So emotion is something that is claimed to be super important for making authentic music or authentic visual art. So I have sort of a wonder there if any improvements at AIs that are generating this artwork, especially there's projects at DeepMind where they interact with someone to, I think it's called AI Duet actually. And there's a person who's playing along and then the AI is improvising with the person. And so maybe through that interaction, they're feeding off of some sort of emotional state of the person. And if that's anything that you guys are interested in for your project. But then I have a second question, sort of where your talk ended, about how the AI needs to learn the emotional, sort of starts to learn the emotional patterns of the person that they're working with. And it just made me think, we do have pets already, and they already have, embodied interoceptive states that they're responding to, and they're responsive to, your emotions. And we have therapy pets that, therapy animals that are responsive to your emotion and also can nudge you into different patterns of behaviors. So I wonder whether these maybe affective robots would be looking something like therapy pets, or would be looking something like surveillance that's reporting back to a doctor or something.
Yeah, really, really interesting. On the point about art, I don't know if I've got anything really substantive to add to what you already said, but to the question, are we interested in it? Speaking for myself, yes, definitely. I kind of have a background in aesthetics, and so I'm really interested in what active inference and prediction error minimization has to say about creativity generally. I'm not sure it would fit into this particular project that we're doing now. On the topic of therapy pets, yeah, again, a really good point, something I've not actually thought of. I'd have to think about the kind of dynamics between, because I actually don't have any pets, unfortunately. I've never been able to, but I have made use of kind of therapy days with animals. But I think you hinted at something in your question, which is that the devices that we're talking about, I think they'd be able to engage with their users on a much more level playing field. I think with the therapy pets, the therapy animals, in my experience, it's always at least felt like kind of a kind of one-way street, maybe. The animal with if you could have a device that was, like you say, also plugged into kind of mental health services that have been run by humans, or it had access to certain information, it could look out for certain bits of information in your speech or whatever you're inputting into the device. And then it could, like you say, then connect with other healthcare professionals and get you any help that you might need. So I think there would be benefits that come with this kind of technology, but I think it's a really interesting point. I don't know if Mark's got anything he wants to add to that.
No, I think that was great. I just agree. I think everything you said is what I would say as well. Very good.
All right, cool. So then I think we have Jonas. I think he wants to, yeah. So yeah, go for it.
Hey, Ben, thanks so much for the talk.
Hey, Jonas,
so much appreciated. There's just two thoughts coming to mind in the talk you have. I would just kind of be keen to share them and see how they land. One of them is, and you hinted at this a bit at the beginning, kind of how emotional interactions work. And that's not only kind of a picking up of emotions, but often like a specific kind of teasing out certain emotions. So engaging in certain actions. So it's like actively seeking for certain responses. And I wonder how that fits into this broader image. If you've thought about the mechanisms by which that would happen, or if that kind of fits into the whole thing. And maybe I just put the other thing out there as well.
Actually, Jonas, if you can hear me? Yeah. What do you think there? Because of course, like if you have a technical idea about how that gets unpacked, I'd love to hear it. I mean, that was your question, right? Like, were you thinking about how we specifically implement some sort of active, emotional information foraging? I mean, if you have an idea, I'd love to hear it.
And so that links a bit into the second part, where you talked about the duet for one and how we kind of dive into the synchrony with others. And one crucial idea there, and that's but what I'm working on at the moment, is that we try to kind of use the same generative model we're in to interact with others. So in the terms of like robotics and robotic interactions, we would put ourselves in the shoes of that other thing. And that's, I think, why embodiment becomes so important, facial expressions like body movement. And so I think what would be super interesting here is to kind of dive into this idea of making it as easy as possible for us to kind of step into the shoes of these robots. And that wouldn't mean to make them as efficient as possible, but make them as human-like as possible, right? Have all the flaws, all the kind of shortcomings that we have. Because if we would have that, then it would be much easier for us to also kind of simulate where the robot is, and to simulate what stimuli could we present that robot to tease, like get better ideas of where that robot is. And so it's so I hope that makes sense a little bit. So the idea is to kind of align them in a way that we are able to figure out what would be the information that, or what reaction would I elicit given certain encounters of information, to then kind of have that simulation again of like knowing how I would respond helps me then interpret the robot. It's a bit wordy, but
Ben, do you mind if I go first? Oh, so
no, go for it. Not at all.
Just two things there. So one, and I think Mao is making this point as well in the chat, if I understand what they're saying there. So the one problem there again is that there might be an overgeneralization of what an external sort of posture would mean for an internal state, and the AI is only going to be able to infer from the external state. But I don't think that that's necessarily a problem. I think it would be really interesting. We haven't done it in this paper, but I think it would be really interesting to think about these things in the way of simulation theory, and to think of the ways that we do learn a lot about each other, and we learn a lot about context by mimicking. I mean, we do that, right? We mimic each other as part of gaining fluency. So again, like one of the ways that you could entrain two models to become entrained is you literally mimic each other. You physically mimic one another. So I think it would be as a sort of just somebody who's just starting on this research, it sounds to me very intuitive to think about what simulation theory type approaches to empathy, how they could be expressed using these same sort of ideas. I completely agree.
And then there is, just as a thought, like a really interesting overlap with the work that Guillaume and the hyperscanning people are doing here, but also at UCL, right, where it just yesterday I've been in the lab and trying out the first few experiments, and just the idea of like just physical kind of modeling and following each other already leading to some kind of neurophysiological synchrony. So that kind of feeds in really nicely to the work you're proposing here. And that's
I completely agree. Yeah, that would be a really exciting. It would be a really exciting collaboration to look at hyperscanning with these ideas. Agreed.
Cool. Hey, looking forward to see where this goes.
Perfect. So is there anybody else who has got a question? Please come to the Q&A. All right, Stephen, go for it.
Thanks. Okay, can you hear me?
Yes.
Yes.
I was just wondering if when you're looking at these emotions, whether you're going to try and look at them in a particular type of niche environment. So for instance, I don't know, maybe when someone's at a fun fair, or when they're in a prison cell, or when it's a practitioner deeply immersed in dance or something like this, is there, so that you know where their orientation, position, attitude is, and how that might need to be somehow sort of established so that you haven't got too much other unknowns going on.
Do you wanna start on that one, or do you want to?
Yeah, I mean, I think it sounds to me like what you're talking about there is the importance of context. If I'm hearing you right.
Yeah.
Yeah. So yeah, I mean, we think that as I said in the slides, I think that perhaps the most important thing in regard to these devices is context. So this is one of the major stumbling blocks of existing emotion recognition technology, is it doesn't take any of that kind of stuff into account. And so this would be an actual, really crucial part of this picture. And I think that it's just played into by things like real embodiment and active vision, so that the more able the device is to act in an embodied way, the more able it is to kind of drink in all the relevant details. And then if there's still prediction error that needs to be minimized, then it can kind of act to prompt and prod whatever the users happens to be doing in whatever context. So yeah, I think that's context might be the biggest challenge in regard to building these devices. And I think, like I mentioned at the end, there's a kind of trapdoor in terms of this, where the better that the device gets in regard to learning about an individual user, the more kind of locked in it is to the sort of attitudes and foibles of that particular user. So these devices would be less general, I think, than we might want current iterations. We might like to think that current iterations are. There's always going to be some payoff there. I don't know if you've got anything to add to that, Mark. No,
that's great. I mean, yeah, it's exactly the point where we're struggling with, Stephen. So I mean, you hit the nail on the head. And yeah. I think the interesting thing that's going to come out of this paper is that we're proposing a way. We're not going to be able to answer exactly specifically how do you deal with this context rather than that context. But what we do get is we get a framework that starts with context. I mean, that's what active inference is all about in a way. You start perceiving and acting based on a model of how the world works. So you're building up a model of the world, including these different contexts, and that's what governs your behaviors and your perceptions. And then what you get in addition is you get AI devices that are good at probing in that context to see why it's different than the other contexts it's shown up in before. So rather than just taking a scowling face and saying, oh, that person is a scowly person, through probing, through actively probing, and through some of the second order information dynamics that we're suggesting, we think that we'd be in a good place to start seeing affective devices be able to be more sensitive in different situations, because it's going to be checking. And when it gets the error back that, oh, I checked and I got a weird error back, last time they looked like that. Like last time they had a frowny face, they were in pain because we were in a hospital. And this time they have a frowny face because they're bored. And that's something that AIs don't do good at all right now. You're working on these big data sets, so they just take a basic emotion, match it over, and say, oh, so-and-so is disappointed. But lots of people look disappointed even when they're not disappointed on the inside. So how do you get past that front layer? And we think that some of these anticipatory, action-oriented, anticipatory and second-order tuning mechanisms would help an AI be able to probe more deeply and start solving some of those context problems, although we don't know exactly how that looks, if you know what I mean.
To get away with not needing to look at the face as well, because you've got other...
Agreed. And we do that all the time, right? I mean, you don't necessarily take cues just from a face. People have really good control over their faces sometimes. You look instead, what's the scene like? What's been happening? And how are you speaking? What kind of word selection are you using? I mean, we know, if you're married or if you're in a long-term relationship, you can tell if something's wrong with the other person by lots of little factors, and then what do? Well, you don't just, if you're a good partner, you just don't assume and say a bunch of weird stuff, but you probe a little, right? You say, what's going on? Like you might have an AI here that will say to you, like, is everything okay, honey? Like what's up? Because your word choice there was different than it normally is in this kind of context. Anyway,
there's some really interesting philosophical work on what's been called affective atmospheres as well, which I think is kind of relevant to what Mark was just talking about, where, when you kind of walk into a room and you can just feel there's a kind of tension or there's a mood, that's present in the room, and you don't look at each person's face and then kind of run a calculation. And I think it's interesting to kind of examine this from a phenomenological perspective and ask what actually is going on in these situations, because then we might, by kind of examining that, we might find out kind of things that are very relevant to designing these kinds of devices, right? If we can really unpack what it means to be in an affective atmosphere and what contributes to that, and I think that's going to be another piece of the puzzle.
Cool. Thanks very much. This is great work. Take care.
Thank you.
Stephen, great questions. Thanks for that.
Super cool. Next in line, we have Kevin.
Hello. So I'm not, I guess it's kind of a not fully articulated question yet. I'm going to kind of work through, but the idea that came to mind was, and again, I don't know if this is empirically grounded, but I think Joscha Bach made a comment about kind of difference between like an artist and a craftsman, right? And maybe this goes back to how do you deal with certain contexts or certain dispositions in an environment. But like, it's maybe a question about the minimizing of prediction error and how helpful that might be in situations where, let's say like the artist is not actually trying to minimize their loss function or to improve their conscious state, but to, as best they can, represent it, right, through their art and express it in that form. And they're not actually trying to improve their experience. Does that kind of make sense? Like, so I'm kind of wondering what y'all think in terms of those situations where people are not trying to actively improve their experiences, but they're actually trying to represent them or to somehow savor them. I'm not sure if that's the right word, but hopefully that can lead somewhere.
Are we talking, so when you say they're not trying to improve, they're trying to savor something, is this again about creativity or maybe even play?
Right, but like play at the expense of the player. Like, so they're not trying to, let's say, minimize their uncertainty. And I'm kind of wondering, like, from a theoretical standpoint, like what does the active inference framework do in that kind of context, if that makes sense?
I think so. When you say play at the player's expense, could you say just a little bit more about what you mean by that?
Well, okay, yeah. So maybe it's like someone who's composing a song or a poet who's writing a poem, and they're actually simulating and going through a process that's incredibly internally painful for them, right? And so I'm kind of wondering what is the dynamic that y'all would expect from an active, emotional, like artificial intelligence that's trying to feed back into this. Like, wouldn't it kind of fit to where they're at and just kind of reinforce the negative conscious state?
I see what you're saying. Yeah, this is brilliant. So so if I'm hearing you right, you mean that sometimes we can have emotional experiences that might have a kind of negative valence in the moment, but are actually kind of if you zoom out slightly, they're kind of in service of something productive or something that might be more positive on a larger scale. Is that right?
Yes, and then I think that's in the right direction. I think that's starting to form the question that maybe I have the intuition for.
Yeah. So I think the question's about how might these devices be sensitive to some of these much more kind of mysterious and nuanced instances of human emotional experience where, I suppose, Mark, you've done some work on scary films, haven't you? Fear, because I think that sounds like it might be.
Yeah, because I don't know if this is that on for you, Kevin, but it really is something that Ben and I talk a lot about, because we think one of the big problems with AIs today is, well, not just AIs, but actually lots of parts of our society, is that we have a misguided understanding about what's best for us, And one of those things is we feel like we want things to be easy and optimal. This is coming out a lot in our work on uncertainty. You might think that an uncertainty minimizing organism would want no uncertainty. It can sound like that at the front, And actually, sometimes it feels like that to us as well. Somebody comes to you and says, "I've got a great idea. I'm going to make this city extremely efficient. I'm going to make it as efficient as possible. You're not going to run into any problems." And you might just think like, "Oh my God, that sounds amazing. Build that." Okay? Except for when city planners really do think like this, and so do AI designers. When you build a city that's stripped down and made optimal, everybody's depressed. You have skyrocketing cases of depression in those areas. And then when you implement guerrilla gardening and provocative art installations and more windy roads and more diversity, lots of diversity, a lot of differences that you have to manage. So error goes up, but depression comes down. And one of the reasons is because we do best when we're in that optimal zone, not too little error, not too much error. If we want to be good at reducing uncertainty over the long term, then we benefit from hugging these good slopes, from these good places where there's a good kind of error. Yeah, so we get better when we're able to select the right problems rather than getting rid of all of the problems. We don't build AI like that today, really. I mean, you go to a search engine because it's most optimal, it's most efficient, it gets you exactly what you expect when you want it. But that's also creating filter bubbles and echo chambers and all sorts of other problems. So how do you solve that? I mean, it's difficult to know. But
well, I think I will say, so one thing that springs to mind is, I mentioned Lisa Feldman-Barrett's criticism of these systems and her criticisms based on a criticism of what she calls the theory of basic emotions. And I think what the kinds of things you're talking about, Kevin, really show why so many researchers are worried about this theory of basic emotions, because it kind of chops up emotion into these very basic categories like fear, disgust, happiness. And really, I think most people know that these just fail to capture the sort of broader spectrum of human emotional experiences. And like Barrett has argued, emotions are actually much more dynamic than that. So she proposes a competing theory where emotions are kind of constructions that are there to make sense of very contextually complicated situations. And so it kind of, I think, at least the way I'm thinking about what you asked, it just brings me back around to context. I think that so far, research in affective computing has really, really not grasped just how important and deep and complicated context is to human emotions. And I think once we start taking that into account, then I think we might find a way for these devices to get a grip on the kinds of situations that you're describing, which really are kind of unique and a little bit mysterious.
Kevin, if you wanted to probe this one step further, on your own, just so you know, we have a paper about to be accepted as a preprint out called "The Predictive Dynamics of Happiness and Well-Being," and in that we propose that these emotional regulation processes are happening at multiple levels. So we have global aerodynamics and local aerodynamics, which I think is a nice step in the direction of increasing these ideas of contextualization. And Alejandra and Bruno, Alejandra's here with us tonight, that we mentioned their paper in our talk today. They've done fantastic work on building some of these into robots, and they were onto the same idea about this layers of affective control, local and global. So that what you get out of that is you can locally fail at being able to manage error well, but globally succeed. And there's a real benefit from having precision be set by more global considerations, so that you can fail at playing a guitar song, but not think your life is a failure, right? You can fail locally, but still feel good globally. Anyway, if you're interested in that, then there's a couple of ways you could go and look at more.
All right, Mark,
thanks so much.
Sorry to interrupt, but we do have time for one last question. And these are the very last 5 minutes before the next talk. And Serval's been standing in line, so I'm just going to let him go ahead and ask a final question.
Do you understand me now? Okay. So I want to raise, like you talked about the issue of inclusivity with the automated emotional processing AI. I want to point out another, which I think is even more foundational ethical issue with artificial empathy. And I'd like to see if you have ideas or propositions or ways to defend the problem. So I think you will agree to two things. The first is that all emotions are socially laden, like you do not have emotions outside the context of certain norms and institutions and values. And second, empathy is to provide empathy to someone is a way to reinforce whatever behavior went into the empathy. So because of these two reasons, if we code robots that provide unconditional empathy, they will provide unconditional empathy to, I don't know, murderers, misogynists, and Nazis, and they will reinforce those norms. So that's not acceptable. But if you build norms within empathic robots, and you agree that some institutions have the capability to say what is literally acceptable thought or not, you get into a 1984 scenario where whoever the fuck gets control, literally, like very literally controls what people think privately. And this is also unacceptable. So do you see a way forward in some sense, or a reason why this problem is actually not so critical?
Yeah, they're great points. I think the first point you mentioned, again, if I heard you right, was essentially that these kinds of embodied machines would also be embedded very much within a culture. So machines that are sensitive to context in this way would also be sensitive to taking on whatever prevalent norms and conventions there were in the culture. I wish I had an answer to this. I mean, there's some very big. I know Rosalind Picard from MIT has given some talks on the kind of politics of affective computing. So if you're interested in these kinds of questions, it might be worth chasing some of her work up and seeing what she says on it. I think when we're talking about the dangers of this kind of technology essentially falling into the wrong hands and having very powerful entities install norms and conventions in these machines that would then potentially, the point I made in the presentation was about manipulation, because obviously if there's model synchrony between the device and user, one of the pitfalls there is that the device is going to be much more apt to manipulate the user's feelings. And so, I mean, all I would say really is I think you've made great points, but I don't know, I'd have to think much more carefully. I wish I had some answers to those worries, but I just don't.